Hello and welcome to this AI Weekend Hack project. The vision for this video is to show you how to take an image of a car and then teach a computer to localize the number plate. So basically you have an image of a car like I have here, and you want to teach a computer to be able to um, localize the number plate. So it's going to focus on just the number plate, and then we go a step further to learn how we can use another Python library to be able to read the characters on the number plate. And this number plate localization technique is very basic, and the reason why I'm saying it's basic is because I'm using traditional computer vision techniques. Ideally, in the face of deep learning, you want to go in the direction of deep learning, but unfortunately, if you don't have a lot of data sets that you will use to build a deep learning model to be able to identify the region of interest in a car, which is in this case the number plate, then you have to start off with traditional computer vision techniques. And another reason why this is not too bad a solution is that once you have a traditional computer vision um, solution, that can serve as a baseline with which you compare your deep learning solution. Okay, so I'm actually working on getting a data set of a large number of cars with annotated regions around the number plate, but until then, this should give you a starting point if you are interested in picking the image of a car and then localizing the number plate and also reading the characters on the number plate. So let's start by showing you how to set up your environment, install the libraries you need, and then we'll hit the road running. So I have my terminal here, and I'm going to create a folder. So I'll say mkdir. I'm going to call this automatic number plate recognition. So ANPR. Okay. Then I'm going to cd into that ANPR. Okay. Now I want to create a separate Python virtual environment so that I don't install the libraries in my global Python path. So I'm going to spin up a virtual environment here, and I've explained the virtual environment in some of my videos, but if you don't know what a virtual environment is, it is basically an isolated Python installation per project. So if you're working on 10 projects, you are free to create 10 Python instances so that each one of them have libraries that are uniquely important to the project you are working on. This way you avoid installing libraries in your global Python installation. Okay, so I'm going to create it by saying Python 3 minus m vmv, and I'm going to call it env. So basically what this command is doing is it is invoking a module in Python called venv, which stands for virtual env, and I'm creating my own virtual environment in the folder, the ANPR folder called env. So if I do ls, you see that there is env in there. Now to use this isolated Python instance, I need to say source env bin and activate. So now if I say which Python 3, you see that it is pointing to the Python instance in the ANPR project folder. Okay, so now that we have our virtual environment set up, the next thing is to install the dependencies that we need for this project. The first one we're going to need is OpenCV. So I'm going to say pip 3 install OpenCV Python, and then you give it a while and it's going to download OpenCV and it's going to install it in your virtual env. So this is done, and OpenCV also has another package called contrib. So I install OpenCV contrib Python, and this has also been installed. Now the next dependency that we need is matplotlib, because we want to be visualizing how the computer vision techniques we apply to our image is transforming the image, and it is going to help us to understand what each step in the processes we follow to segment out the number plate does to the original image. So we are going to use matplotlib to plot the images side by side. So I'm going to say pip3 install matplotlib. Okay, so matplotlib is also installed, and just so this tutorial is interactive, I'm also going to use Jupyter notebooks. And the reason I want to do that is so you will see each instruction and the immediate effect that it has on the task at hand. So I'm going to say pip3 install Jupyter notebook. I think Jupyter is enough. So this is also downloading Jupyter, and then once the installation is done, we will start Jupyter notebooks, and we can start working on our interesting idea of localizing number plates out of images of cars. Okay, so this is done. So I'm going to say Jupyter notebook. So this has started the Jupyter notebook server for us, and so here we are in the Jupyter notebook environment. The next thing I'm going to do is to copy the image of this car into the folder where our code is going to reside, so that it is easier to access it in code. So I'm going to go to the other section of the terminal, and I'm going to go into project ANPR. Okay, and then I'll create a folder here called images, and I'm going to paste the image of the car I copied in here. Okay, so now if you list, you can see that we have the env, that is a virtual environment, and then we have the images, and inside the images we have the picture of the car that we are interested in teaching the computer to localize the number plate from. Okay, so over here I'm going to create a new notebook, Python 3. I'm going to call it number plate localization, and this is our notebook ready for us to use. As always, I'm going to start by importing all the needed dependencies that are useful for the task at hand. So I'm going to import OpenCV. I'm going to also import NumPy. And just in case you're wondering how we got NumPy, NumPy is a dependency for both OpenCV and Matplotlib. So once you install any one of them, NumPy is automatically installed for you. And I'm also going to import matplotlib.pyplot as plt, and I'm going to instruct matplotlib to be inline. So matplotlib inline. So basically what this line is going to do is going to let Jupyter notebooks render our graphs inside Jupyter notebook, as opposed to the other approach where Matplotlib is going to open its own window to render your graphs. Okay, so this is basically what it does. And two more things that we need, two more dependencies that we need is the OS package and the random. No, okay, I'm not going to use random, so I'm going to just import the OS because I want to be able to read from the image file. So I'm going to import OS. Okay, so I've imported all the libraries we need, and there is one more thing I forgot to install. I need to install PyTextEract because we're going to use that for reading images, reading characters out of images. So before we continue, I'm going to install that as well. So to do that, I'm going to source bin activate, because they are different sections of the terminal, so I need to activate it here as well. And then I'm going to say pip3 install PyTextEract. Okay, so TextEract is also installed now. To confirm that, I'm going to import TextEract also here. So I'll say import PyTextEract, and let's see if everything is okay. Yeah, cool. So we now have all the dependencies we need, and we are ready to get started working on how to localize number plate out of an image. Just in case you're wondering which version of OpenCV I'm using, you can print it out by saying cv2 dot version. Okay, so this is OpenCV 4.1.0. Okay, now the first thing we need to do is to read the image, and with OpenCV, once you read an image, you have it as a numpy array. Okay, and that is the more reason why we have numpy imported, and we might not directly use it, but once OpenCV reads an image, we have it as a numpy array. So I'm going to read the image, but before I read the image, I want to create a function that we can use to plot two images side by side, and the reason will become clear afterwards. I want us to be able to look at an image before we applied some particular computer vision operation on it, and then the image or the output of that, the result of that operation on the image, okay, so that we can compare it side by side, and it's going to help us to understand how things are really working here. So I'm going to create a function called plot images, and it's going to take image 1, image 2, and just in case you want to give titles to it, to each subgraph, so I have title 1 and title 2, and by default they are nothing, so you can either pass or you leave them empty. And I'm going to create a figure with matplotlib. I'm going to create a figure, and I'm going to give it a figure size of 15 by 15. So that is how big I want my graph to be. And I'm going to say axis 1 is equal to figure dot add subplot. So I want two columns of graphs, or two columns of axis on one figure. Okay, and to do that in matplotlib, I'll say one row, two columns, and I'm targeting the first column on the row. Okay, so that is the reason why I have 1 to 1, and then I can say axis.im show, and I'm going to show image 1 here, and I will show all my images as grayscale, because converting images to grayscale helps you to helps the operations to be much faster, because it doesn't have to deal with multiple channels of colors. Okay, then over here I don't want any text on my x-axis, so I'm going to give it empty, and I don't want any text on my y-axis, so I'm going to make it empty. And if you give me a title, then this is going to be title 1 for the first axis. Now I'm going to copy and then change this for axis 2. And over here I'm going to show image 2, title 2, and my target is going to be the second column of the row. So good, now we have a function defined that is going to help us to plot images side by side. Now the next thing is to actually read the image and then get the numpy array. So just to see where the image is, it is in, if I go to images, there is a file called car1.jpg. So I'm going to say path is equal to, so this notebook is here, and then is in the same folder as images. So I'm going to say is equal to dot slash images slash car, what's the name again, car underscore 1.jpg. So car underscore 1.jpg. Okay, so we have the path to our image already defined. And so we go ahead and we say image is equal to cv2.imread. So this is the point where I'm reading the image. And once this is done, I'm going to have a numpy array. Okay, so I have read the image into a numpy array. How do we know that this has worked? That is why we have the plot images function. So I'm going to say plot images, and now I'm going to plot the same image twice because I haven't done any operation on it. So I'll say image and then image. I don't want any titles. So this is the image of the car that we loaded, and I don't want any title, so that is the raw image. If I wanted titles, then I can say title 1 is equal to original image. I'll just say original, and then I'll say title 2 is equal to original because I've not done any operations on it. So we have our titles here, and then it's the same image of the car that I showed you before the start of this notebook. Okay, now I mentioned earlier that in computer vision, most of the time you do your operations or manipulations of the image on the grayscale version, because a colored image, as you know, have 3 channels, and it is not always important which channel you are dealing with. The most important thing is the structure of the image. So most of the time you convert your images into grayscale before you apply most of the computer vision techniques on it. So let's go ahead and then do that here by saying gray is equal to cv2 dot convert color, that is cvt color. Okay, and then you pass in your image and you say cv2 dot color bgr to gray. Okay, so now we have a grayscale image and we want to plot it side by side with the original one. Unfortunately, we might not see a lot of changes here because my plotting function is plotting everything as grayscale already. So I'm going to plot image and I'm going to plot the grayscale one here. So this is the original and I'm going to plot the gray. Sorry. Okay, so as you can see, on the left is the original image that we read from the file, and on the right is the image that has been converted into grayscale. So grayscale images have values ranging between 0 and 255, and 0 means black, 255 means white, and anything in between 0 and 255 is a grade of a shade of gray. Sorry, was I going to say a grade of shade? Okay, so now we have our grayscale image. The next thing we want to do is to perform an operation on the grayscale image that is going to remove some of the details from the image but still maintain what we are interested in. But before we do that, let me explain to you how this whole thing is going to work. So if you look at this image, the image of this car right here, we are only interested in this section, that is the number plate section. Okay, but apart from what we are interested in, there are a lot of things that we consider as noise, even on the car itself, like the crown of the Audi here, the boot of the car, this windscreen, and all these bicycles in the background and stuff. We are not interested in those things. We are only interested in the number plate. So it is not much of an issue if we perform an operation that is going to ignore some of these details, the bicycles and the background that we are not interested in. And one such operation is blurring. So you blur the image a little bit so that the background is not so much detailed as it is in the original one. Okay, so I'm going to create the blur image and I'm going to say cv2 dot cv2 OpenCV has a lot of blurring operations, but I'm going to use the bilateral filter. So I'm going to pass it the gray image and then These are some kernel sizes that you specify for OpenCV to use to determine how it convolves over the image and then performs the blurring operation. I mean, for details of these things, it will be important for you to Google them out. So basically, I can come here and then say CV2 dot bilateral filter. And I'm sure once it points you to the OpenCV documentation, you'll be able to understand what each one of the parameters stand for. Okay, so I'm not going to explain that. I'm going to tell you the effect of the operation on the image, but for more details you have to consult so that I can keep this video short. Okay, so what is that? CV2 has no attribute bilateral filter. I didn't spell something correctly or what. So CV2 dot bilateral, not trial, it's trial. Okay, cool. So now I have my blurred image, so I'm going to plot it side by side with a grayscale one. So I'll say gray, I'll plot the blur, so gray, and then the blurred image, and let's see. So if you look at this image now, you can see that on the left we have the grayscale image that we had originally after converting color to BGR to gray, and on the right we have the blurred version of the same grayscale image. Now if you look carefully, you can see that the bicycles and the background is not as detailed as we have in the grayscale version. However, our region of interest has not been touched. We can still clearly see that the number plate has the characters 3J0H22A. So we have not distorted the image beyond the point where it is practically useless for the task of localizing your number plate. So this is cool. You can play with the parameters and then change it. I mean, this is more of trial and error until you find what works best for you. And the reason why the deep learning approach will be much better is you avoid trial and errors, because like deep learning is going to help you to learn a function that is going to take an image and give you the region of interest that is your number plate. But I'm going to make another video on that once I am finished with preparing the data set. Okay, so now we have our blurred image. The next thing we want to do is what is called edge detection. And what edge detection does is going to run some filters across the image horizontally and vertically, and it is going to return an image that only has the edges of the image. So like it is going to remove all the details, like the blackness of the car, and the whiteness of the number plate, and the color of the background, and the color of the sky. I mean, all these things are not important to us when it comes to localizing the number plate out of a car. Okay, so the way I want you to think about edge detection is imagine you ask a kid to draw a car. You know, they are not going to be able to draw the car with all the details, and yet still when you see the edges of what they've drawn, you will be able to discern that they were actually trying to draw a car. That is how we all start learning how to draw. Okay, and it is not too useless. It is actually useful because the edges are what informs us of even what we are looking at is the edges. So if you drew a house without coloring the walls and the windows and the doors, every human being is still able to discern that you were attempting to draw a house. In the same way, OpenCV has an operation called canny edge detection that applies to the image and gives us the edges of the image, because of course we are not interested in the blackness of a car. The blackness of a car or the color of a car doesn't affect where the number plate is located. I mean, If I see a yellow car, I can still tell you where the number plate is. If I see a green car, I can still tell you where the number plate is. So I'm going to get only the edges by saying cv2.canny, and I'm going to apply that to our blurred image. And again, you have to provide some parameters, which I would advise that you look up to understand what these parameters that, because like if I say I'm going to explain how canny edge detection works and why these parameters, actually I got them by trying different values, and then I got what works for me. Okay, so you look it up online, you read more about it on the OpenCV documentation, and you understand what is really going on here. But the basic idea is when I apply canny edge detection, it is going to give me only the edges of the image. Sorry, this is not CV3, CV2. I'm ahead of everyone. Okay, so now I'm going to plot my blurred image alongside the edges. Okay, so I'll say blur and then edges. Okay, so sorry. So like I explained earlier, this right here on the right is the result of applying canny edge detection on an image. And honestly, if you saw somebody make a drawing like this, you can actually know that the person is trying to draw a car, like without all the details. So the edges is the most important thing we need for our localization, and that is why we applied edge detection on it. Okay, so I'm going to recap up to this point, and then we continue from here. So we started by loading our image. We converted it to grayscale because of course it makes some of the operations faster and easier, and we applied bilateral filter to the image so that we will denoise it, or we're going to remove the details of the background and some of the things that are not so important to us. And after blurring the image, we applied canny edge detection so that we get only the edges of the image. Okay, now we have gotten to the core part of being able to localize the number plate out of the image, or I'm segmenting the number plate out of the image. And the way this is going to work is we need to find the contours, okay, the contours in an image. And for this, I want you to see the definition of contour. So I'll say I'll Google for contour detection in OpenCV Python, and I think their documentation has a very good definition of what a contour is. So contour. They have a definition of contour somewhere here. Okay, let's see contours getting started. So it says contours can be explained simply as curves joining all the continuous points along the boundary having the same color or intensity. Okay, so in our the result of the canny edge detection, you can see that we are still able to see the number plate, and it kind of looks like it is bounded by a rectangle. Okay, so that closed figure around the region of interest is what is known as contours. And the reason why they are contours is because they are adjacent each other and they have the same color or the same intensity. So the next step is to determine all the contours in the image. And once we have the contours in our image, we will be able to think about how best we can figure out which contour is going to help us to best approximate where the number plate is on the image of the car, because all these edges have contours. Okay, so it's not just the number plate. If you look here, this is a contour. Any closed figure that is bounded by a path that has the same color or intensity is known as a contour. So in OpenCV, we have a function called find contours, and then you give it an image, and OpenCV is going to run certain mathematical operations on the image, and at the end of the day it's going to give you a list of xy coordinates, okay, xy coordinate that like closed, so closed xy coordinate that are, I mean, boundaries around certain regions in your image. So I'm going to say contours new is equal to cv2 dot find contours, and I'm going to write code here, but I will explain to you after. So I'll say cv2 dot list and cv2 dot chain approx simple. Now let's go to the OpenCV documentation and see what they mean. So it says it takes three arguments. The first one is the source image, the second is the contour retrieval mode, and the third is the contour approximation mode. I mean, these are all hiding behind the scenes some mathematics that is performed on the image to be able to determine all these xy coordinate that are that bounds certain regions of the image. Okay, so like I said, the best way to understand all these parameters is to look at the OpenCV documentation, because it is hard to even remember them offhand, but once you know what they represent, you know how to tweak them to get the work done. Okay, now in writing my code, you saw that, where is it? In writing my code, you saw that I said find controls, and I gave it copy of the edge, the edges of the image. And the reason I'm using a copy and not the edges itself is because the find controls operation is destructive. Like, it permanently changes the image that you give it. So in order that we will still have the original result of the edge detection and still be able to do contour detection, we give it a copy so that it doesn't destroy the original image. Okay, now this cv2.find controls returns multiple parameters, like three of them, but what we are interested in actually is the contours here. It has hierarchy and all those things that are important, but for now we are only interested in getting the contours. So I'm getting the contours right here. So let's run this, and now we have contours. Let's see the type. So like I told you, it's a list of lists. Okay, it's a list of lists. Like let me actually make it clear to you. Let me print contours, let's say 0. You can see that contours 0 is also a list, and sorry, it's also a list of lists, and each of the entries in here represents an xy coordinate that binds a particular figure in the image. So this means that the first contour itself is a list, and the contours variable is actually a list of lists. So if I take any list from the contours, it's giving me a figure that is binding a particular structure in the image. Okay, so I'm going to get rid of this, and we want to visualize the contours that were detected on the image. Okay, we want to visualize the contours that were detected on the image. So I'm going to do another OpenCV operation that is also destructive. Like, it draws the contours that have been detected onto the image itself, and the way I'm going to do that is to make a copy of the original image. So I'm going to say image copy is equal to image dot copy. Okay, so now we have a copy of the original image we read from the file, and the next thing we want to do is to say cv2 dot draw contours, and I'm going to do that on image copy and I'm going to draw all the contours that were found, and I'm going to explain this code as well. So I'm going to say 2550255, and I'm going to draw this with 2. Okay. Now, the draw contours operation takes the image, the contours that were found by invoking the cv2.find contours, and because contours is a list of lists, the draw contours has a parameter that tells it which contour you are interested in drawing. Now, if you specify -1, you are trying to tell draw contours that I want you to draw every contour in the contours variable. The next parameter is the color with which you want it to draw the contour. So like I said, all these are contours, and once we run this cell, you see that it will draw them with the color we've specified. Over here it is RGB, so I'm saying 255 red, 255 blue, so I don't know what that color is, whether magenta or whatever. And then the last parameter is the width of the lines that you wanted to use to draw the contours. Okay, so like I said, draw contours, find contours are destructive. That is why we give them copies of the image. So I made a copy of the original image, and now I'm going to visualize the original image and the contours. Okay, or let's visualize the edges, and then we drew on the image copy. So image copy, and then I'm going to say edges and then contours. So let's see. Okay, sorry. So as you can see, the find contours operation found all closed boundaries that are surrounding figures in the image. So as you can see, this looks kind of like a rectangle, a triangle. This looks like some polygon, and the bicycles and all those things had contour in them. So you see, this is why it is important for us to do this filtering to remove some of the background details. Otherwise, it would have found a lot of contours here, and then it will be the work of localizing the number plate will actually be harder. So like I said, you can even play with these parameters, change 90 to 120, 150, and then see how best it distracts the background. And still, the most important thing is still choose figures that distract the background. They destroy the background massively, but still has least effect on your region of interest. And in this task, our region of interest is finding the number plate. Okay, so cool. This is the edges, and we found the contours, and we've plotted the contours. You can see that this is interesting because we still have um, our number plate showing up here. So now we have a lot of contours. In fact, let's print how many contours were found. Sorry, CNTX. Sorry. So in this small image, the OpenCV find contours operation found 194 contours. Out of these 194 contours, one of them is our number plate, and this is where you need to put on your thinking cap and then figure out, if you were given these contours, how will you determine what a number plate is. Thankfully, number plates are always rectangular. Sometimes they look kind of squarish, but not very square. But most of the time they are rectangular. And by being rectangular, you know that the ratio of the width to the height is going to be big. Like if I divide the ratio of the width of this by the height, then it's going to be a big number. Apart from the number plate, there isn't much in this image that is almost a perfect rectangle. So this is the line of thought you need to have. So OpenCV has operations that help us to learn properties of contours, and I think if you come to their documentation, there are contour features, and there are things like calculating moments, the area, the perimeter, the approximation. We actually use the perimeter function and then the approximation function, and once we get there, I'm going to explain to you. So I'm going to close the ones we don't need. And then the next step is we want to sort out sorry, we want to sort out the contours that we found based on the area. Okay, like I explained earlier, you can see that if we calculated the area of all the contours that were found, this number plate, which is our target, will have a bigger area than almost everything that we found here. But of course, it depends on the image you chose and how well you were able to destroy the background and still maintained the definition of the number plate in the image. Okay, so there are times if there was a rectangular wood here, this basic computer vision technique might think the wood is the number plate because it's rectangular, and that is why we would work more with deep learning in the next weekend. So we want to sort these contours. We want to sort these contours by using the sorted function in Python, and is the contours we want to sort by running an operation called cv2.contourArea. Okay, so this is going to calculate the area, that is the space that each of these contours is taking in the image. Okay, and then we want to reverse it. We want to reverse it. I mean, this is pure Python. The sorted function is pure Python. You give it a list that you want to sort, the key with which you want to sort, and the key can be a function. So this function is actually going to be called on each of the contours here, and the value, that is the area that is calculated from each of the contours, is what is going to determine its position in the sorted list. And we want it in the reverse. So instead of small to big, we want it big to small. Okay, because we want to ignore all small contours that are definitely not number plates in our image. Okay, so we've done this, and then now our contours are sorted. Our contours are sorted, and we want to select, like I said, this thing here is going to calculate the area for each of the 194 contours that it found. But of course, not all these 194 contours are possibly the number plate, that like are bounding the number plate. Okay, so here you do, it's more of heuristics depending on the image. So if I can say I'm selecting the first 30 because you are arranging the area of the contours from big to small. So if I select the first 30, then every other thing you are rest assured that is going to be one of these unimportant guys here. So this is a figure that you also want to play with. Okay, it's a figure that you want to play with, and just to see the effect of selecting this number, like so sorting the contours based on area and selecting the first 30, you see the effect it has on the image. Okay, so to do that, I'm going to draw the contours again. I'm going to draw the contours again, and I'm going to make a copy of the image once again because the first one has been destroyed. Okay, so this is going to be equal to image copy, and then I'm going to plot it again. Okay, so I made a copy of the original image, just that I'm calling it image copy because this one, because of the drawing, has been destroyed already. And once I have this, let's plot this in let's say red, or we can use the same color. Okay, so I'm going to plot these two images once more, and I'm not going to plot the edges. I'm going to plot the original image this time around. Okay, to make things simple, I'm going to make things simple, I'm actually going to make another copy. What do I call this? Image copy. I'll say image reduced contours. Okay, and then so that we can plot the two side by side. So reduce contours, and I'm going to plot this on reduce contours. And so I'm going to plot the original image that had the contours on it, and then I'm going to plot the reduced. Okay, so I'll say contours and then I'll say reduced. Okay, so let's look at this image and see, was there any change? Let's look at it carefully to see if there was any change. I doubt there has been any change, so we can come in here and say, okay, we are interested in the first 10. The most important thing is we still have the number plate. So see what happened here. When it was 30, let's go back to 30. When it was 30, it looks as if the the number of contours have reduced. Okay, look at it carefully. You can see that in the first image there are a lot of contours, the bicycles having all the contours and the bounding figures around them and all that. And in the reduced we are selecting just the first 30, and because we are selecting the first 30, it has actually reduced the contours it is finding in the image. And like I'm saying, the most important thing is you still have your region of interest in the image. Okay, in the first drawing of the contours, you can see that the Audi crown and all those guys were selected, but in the second one it is not there. So like I said, you can play with different numbers. The most important thing is your region of interest is still in there. So when I select 10, it doesn't seem to change much from 30, but I mean, that is why I said this is all based on heuristics. You do trial and error, and you find what works best for you. So if I do this, yeah, not much difference. So I'm going to use 10 because it is less expensive computations to be done. Okay, so now we have our image. We've been able to do contour detection. We've filtered the contours and we've selected the one that we've selected the number. We've sorted the contours by area, and then we selected the first 10. So as we can see on the right side of the reduced contour plot, we still have our number plate in there. So how do we go ahead and then segment out or localize where the number plate is in our image? So to do that, I'm going to create a variable called plate, and the plate for now we don't know, so I'm going to say it's none. Okay, then I'll say for C in contours, so we're going to loop over the 10 contours. So this is the 10 contours. As at now, contours contains just 10. Originally it had 194. To prove that, let me just cut this and I'll say print len of contours. Sorry. So now we have only 10 contours filtered by area from the largest to the smallest, and it is still having our number plate in there, so we should be able to segment it out. Now to do that, I'm going to loop through all the contours, and I'm going to calculate the perimeter of the contour. So for each contour, I'll say cv2 dot arc length th or ht, and once again the parameters, you have to look them up on the OpenCV documentation and then see what they mean, but I'm going to open them shortly so that you also get to understand what is happening here. Then I'll do approx poly dp. This function here attempts to count the number of sides, how many sides are in the figure bounded by the contour. Okay, times perimeter, and I'm going to explain this to you shortly. And after that, I will say if edges count is equal to 4, then we found our number plate. So let's come in here and then see what this thing does. So this is called contour approximation, and it says It approximates a contour shape to another shape with less number of vertices depending on the precision we specify. So the 0.02 is the precision that worked for me. You can also play around with different numbers to see what is much better. And I'll keep repeating that this is some of the reasons why deep learning is much better in this regard, because it saves you from having to do this trial and error and still having your solution not perform very well in production because of different lighting condition, camera angles, and all other disturbances in the real world that you didn't encounter. But basically, what this um, approx approx poly DP does is to try to approximate the number of sides or the edges that are bounding your figure. So the example they have given is, if you have this figure right here, depending on the value of epsilon, that is they made mention of it here. Depending on the value of epsilon that you give it. So it says in this second argument, is called epsilon, which is maximum distance from contour to approximated contour. So if a human being looked at this, you will see that even though this is not a perfect rectangle, it is okay for you to be able to draw a bounding rectangle around it. Okay, and that is what this function does. It approximates the number of sides so that you can be able to draw a bounding rectangle around your region of interest. And like I explained, the epsilon 0.02 is what worked for me, and it depends on the perimeter. So you calculate the perimeter. The perimeter is just the length of the line that goes around the entire figure, like from start to end. And so this is this epsilon is multiplied by the perimeter, and then the magic is done in this function and is able to approximate the number of sides. And like I explained earlier, the number one way to spot out the number plate from an image of a car is that a number plate is always rectangular. Okay, we can go a step further by even taking into account the aspect ratio, because like I said, if I have a wooden structure here, if I have some wood in the image that is rectangular, then this solution might think that the wood is also possibly a number plate. You get the point. So we can even go a step further by improving this code to take into consideration the aspect ratio of the width and height. And once we know the standard size, of course, number plates have a standard size globally. So once we know the standard size of number plate and we know the standard aspect ratio, then we can safeguard our solution against some of these unforeseen failures in production. But for now, let's just look for something, because in this image, this is the contour that seems to have approximately 4 sides. Okay, so if we find the contour that gives us 4 sides, then now we can calculate the bounding rectangle, and the bounding rectangle is also calculated with a function called cv2 dot bounding rect. Okay, and then you give it a contour. Now if I calculate a bounding rect, it is going to give me the x and y coordinate where the rectangle starts, and then the width, so that is how far along the x-axis I need to move, and then the height, which is how far along the y-axis I need to move to be able to find the image. So if our code here finds that this region is the number plate, it is going to give us this first point here where I am pulsating my mouse, and that is going to be the xy, and it's going to give us the width that is along this line, and it's going to give us the height that is along this line. And this is going to help us to localize and then crop out the number plate out of the image of the car. Okay, so once we found the bounding rectangle, we can say that the plate is now equal to, so this here is a numpy operation that is helping us to crop our number plate, from the car. So we start from the y, and then we go y plus height, that is the end of it, and then we start from x and we go x plus width, that is along the horizontal. So we are able to get it. And I mean, once we found a figure that is four-sided, we can break the loop, because we don't want to find all four-sided figures. That is why I keep stressing the fact that if we have any other thing that is rectangular in the image and is showing up in the contours, then it will trick your code to make it think that that is also a number plate. So it is important for you to take into consideration. It can be an assignment. You can work on this to improve this by taking into consideration the aspect ratio of the width to the height, and basically that should be it. So now that we found this, we can break. Okay, and once we found the number plate, what we can do is let's write it. Let's write the number plate to the disk. Okay, so I'll say cv2.im write. We found the plate, so I'm going to call it plate.png, and I'm going to write plate. Okay, so let's run this. Oh, what is wrong? Perimeter, I didn't spell perimeter correctly, so I'm going to copy this and paste it here. And what is this again? Edges count. Is it the truth value of array is more than one element? What is going on here? Let me debug this. So, oh, if length, I didn't check for the length, sorry. I didn't check for the length because it's going to give me an array. Okay, it's going to give me an array of the sizes of each side, so I need to check the length. Okay, so now I have my plate. Let's go see if we actually have the plate. So if I do this, you can see that the plate has been cropped out and it has been placed here. Let's see this, if we actually have the plate. So plate, and voila, we have the number plate from the car. Okay, so we started with this image. And we've been able to use traditional computer vision techniques to crop out the number plate. We are not going to end here. We are going to actually read the digits, the characters on it, and then that is how we're going to end. Sorry. So I'm going to plot the plate that we found. I'm going to use the function plot images to plot the number plate that we found. Okay, so I'm going to plot plate. I'm going to plot plate. I'm going to give them title plate, and because they are the same image, I mean, it doesn't matter. I'll just say plate. Okay, so great. We have been able to segment out these from the image here, the region that we were interested in, which is the number plate. So now we've been able to find the number plate. What next can we do? We can go ahead and then read the characters on the number plate. What could be the application of this solution? Well, it could be a parking space, a paid parking space, and then you want to put a camera there so that once the cars are coming in, the camera will pick the number plate of the car, read the characters on the number plate, insert it into a database, and then take note of the time that the car got into the parking space. And when the car is leaving the parking space, there'll be another camera that reads the number plate, fetches information about the car from the database to know when it entered and when it's leaving to calculate the charge. Okay, it can also be for a gated community. If you don't want to allow unregistered cars into the gated community, then what you need to do is you build a database of the number plate of all cars that you want to allow into it, and then you build an automatic gate. So you place a camera there, and when the car gets there, the camera reads the number plate. If it is not one of those cars that are allowed to enter, then the gate is not going to open. But if it is one of the cars that are supposed to be allowed to enter, then it opens for them. So there are endless possibilities with being able to localize and read the characters. So we did two things. We've been able to localize it now. The next thing is for us to read the characters from the image. And to do that, we're going to use PyText Eract. So I'm going to say PyText Eract, and then I'll read the test by saying the test is equal to PyText Eract dot image to string, and then I pass in the image, and the image right here is the number plate. Like, we cropped that section, and you can specify which language your number plate is in. I mean, it's almost always going to be English characters. I don't know what other countries do, but so we've done this, and let's print test. So let's print test, and good. So now you can see that we imported text Iraq, we gave it the number plate, and text Iraq has told us the characters on the number plate. So this is it. We started very simply, got an image, we wrote a function to plot images side by side. We read our image, we plotted them to see, no change, and then we converted the image to grayscale to make the calculations easier. We plotted them to see, and obviously there's color, there's grayscale, and in order to destroy some of the noise in the background, we blurred it out by running this bilateral filter on the grayscale image, and you compare it side by side, you can see that this is blurred out. And the key point here is blur out as much of the noise without affecting your region of interest. And clearly we can still see our number plate, so it's not a big deal. Now, we are not interested in all the details of a car and what makes a car and what makes a number plate. We are interested in the edges that define a number plate. So we ran canny edge detection on the blurred out image, and that gave us this image with just edges, okay? And then the next thing we did is to find the contours, and we drew the contours of the image. We found 194 for different cars and different environments. You find different number, and then we sorted the contours based on area. So we calculated the area of each contour. We sorted it in descending order from big to small, and we selected the first 10. Okay, because I mean the number plate from the graph here, you can see that from the plot here, you can see that the number plate will be one of the things with the biggest area. So I'm sure even if we limited this to 5, we will still find the number plate. Okay, and then we plotted the first contour detection, and then when we selected just the first, then you can see that a lot of the noise have been thrown away. And then over here we loop through each contour out of the 10. We loop through, we calculate the perimeter, and then we use the perimeter to approximate the sides, I mean the length of each of the sides. Okay, so this approx poly dp will take in the perimeter and then an epsilon that is how sensitive it should be, and it is going to give you the length of the sides. And I was only interested in how many sides the figure had, but like I said, we can go a step further to see each of the sides here and then use it to calculate an aspect ratio to be sure that we are finding the actual number plate and not some random rectangle. It could even be a window in the picture and it will say this is the number plate because it is rectangular. Now, once we believe we found the number plate, we stop approximating the size, and then we write the plate, and we visualize it by plotting the number plate that we found that was cool enough, and we leverage the optical character recognition capabilities of Python's TextEract to be able to read the characters of the number plate. So this is it. Very cool, very interesting, nice applications in terms of security, in terms of running a business of automated parking lot, and I mean endless possibilities. So thank you for watching, and I will see you next weekend. Okay.